Hello everyone, in this micro video I will give solutions to some questions I provided in tutorial sessions. I hope this micro video help you to be prepared for midterm and final exams and help you to improve your problem solving skills. The first questions. In the first questions we are looking for the inverse Laplace transform of this given function. As you see here, the order of the polynomial denominator polynomial is higher than the order of denominator polynomial. So we have to somehow divide numerator over denominator. One way is that the tricky method I explained during the tutorial session. However, here I use a classical approach to divide these two polynomials. To do so, I divide denominator polynomial over numerator polynomial over denominator polynomial by multiplying to s squared. The residual polynomial will be s cubed plus 3s squared plus 4s plus 5, which is order is still higher than the order of the polynomial, denominator polynomial. So I do further calculation by multiplying to s, the denominator polynomial by s. I will have the residual polynomial of 2s squared plus 4s plus 5. The order of this residual polynomial is the same as the order of denominator polynomial. So I need to further do calculation. By multiplying to 2, I will have the residual polynomial of 2s plus 5. As you see, the order of this polynomial is less than the order of denominator polynomial. So I terminate the calculation here. So the resulting function will be s squared plus s plus 2 plus 2s plus 5 over s multiplied to s plus 1. Here we have in this fraction we have two simple roots, one s equal to 0 and another one s equal to minus 1. So I will use partial fraction expansion to further simplify this function. Using the partial fraction expansion, I will have s squared plus s plus 2 plus k1 over s plus k2 over s plus 1. I need to find the values for k1 and k2. The value of k1 is equal to s multiplied to the fraction here I have here. When s equal to 0, thus the value of k1 is equal to 5. In similar way, the value of k2 is equal to minus 3. So the simplified f of s is equal to s squared plus s plus 2 plus 5 over s minus 3 over s plus 1. But what you need to note here is that the s power 2 in fact is s power 2 multiplied to 1, and s is s multiplied to 1, and 2 is 2 multiplied to 1. The important point in this problem is that you need to know and keep in your mind that s power n multiplied to fs in Laplace domain is equivalent to nth order differentiation of f of t in time domain. So the Laplace inverse of f of s, by considering this fact, will be, for the first component, we know that the Laplace inverse of 1 is delta Dirac function. Since we have s squared, which it means that we have second order differentiation of delta Dirac function in time domain. So for the third component, we have s multiplied to 1 Laplace inverse of 1 in time domain is delta Dirac function, and since we have s, it means we have the first order differentiation of the delta Dirac function. 2 will be simply 2 delta t. Laplace inverse of 5 over s, 1 over s is the step function, and Laplace inverse of that will be unit step function. So since we have 5 in numerator, we will have Laplace inverse 5, and for the minus 3 over s plus 1, we have minus 3 e minus t. So the final Laplace inverse of function f of s is in this shape. The most important point for this problem is that to know the Sn f of s in Laplace domain is equivalent to n order differentiation of f of t in time domain. The second problem, we are looking for the inverse Laplace transform of this function 1 over s squared plus omega squared. Here we have two polynomials. One is s and another one is s squared plus omega squared. S has a simple root. However, s squared plus omega squared has a complex conjugate root. To solve this one, we have two approaches. The first one is that to find all roots of this polynomial, and but the point is that solving the problem using the complex conjugate is not complex, is not easy task, and it's not easy to deal with them. So I would like to use the partial fraction expansion in this form: k1 over s plus k2s plus k3 over s squared plus omega squared. As I mentioned during the tutorial session, when we have the second order polynomial with complex conjugate roots, it means in Laplace domain, in time domain, we have a function in form of cosine or sine. So I will keep this fraction as a second order polynomial. To find the values k1, k2, and k3, I will use the expansion, partial fraction expansion approach. K1 can be easily find sf of as a multiplication of sf of s when s is equal to 0. So k1 will be equal to 1 over omega squared. For finding k2 and k3 values for the k1 and k2 and k3, I use a classical approach. In this approach, I have the as first I substitute the value of the k1 in this fraction, and for calculating the k2 and k3, I get a common denominator for these two fractions. So by multiplying these two, by adding these two fractions by common denominator, I have this relation. But the point is that the fractions from the right side of the right side fraction and the left side fraction should be the same. Since the denominator are the same, numerator should be the same as well. By putting equal both denominators, I will have 1 equal to 1 over omega squared plus k2s squared plus k3s plus 1. Since in both sides I have 1, this 1 will be cancelled out with each other. So the resulting will be 1 omega squared plus k2s squared plus k3s equal to 0, in order to have the same denominator in both sides. So I put k3s equal to 0. So, thus the k3 value for k3 will be 0, and putting 1 over omega 2 plus k2 multiplied to s squared plus equal to 0, it means k2 is equal to minus 1 over omega squared. By substituting the values k1, k2, and k3 in these fractions, I will have f of s equal to 1 over omega squared 1 over s minus s squared plus omega squared. We know that the Laplace inverse of 1 over s is the unit step function, and if we look at the table, Laplace transform table, we see that the Laplace inverse of s over s squared plus omega squared is cosine omega t. So Laplace inverse of f of s is equal to 1 over omega squared multiplied to 1 minus cosine omega t. Third problem. In the third problem, I'm looking for the solution of the differential equation x double dot plus 2x dot plus 5x equal to 3 when all initial conditions are 0. If Laplace of x of t is x of s, Laplace of x dot t will be x of s minus x0, which x0 is initial condition of x of t, and the Laplace of x double dot t will be s squared x of s minus x0 minus x dot 0, which again x0 and x dot 0 are initial condition of x dot t, and the Laplace of 3 will be 3 over s. So by putting the all initial condition equal to 0, I will have this relation s squared x of s plus 2s x of s plus 5x of s is equal to 3 over s. By factoring out x of s from left hand side, I will have s squared plus 2s plus 5 multiplied to x of s equal to 3 over s. So x of s in final is equal to 3 over s squared plus 2s plus 5. In order to find the Laplace inverse transform of x of s, I use the partial fraction again. Again, here I have a second order polynomial with complex conjugate roots, so I will keep it as it is. So for the value of find k1, I use the sx of s when s is equal to 0, so k1 will be equal to 3 over 5. I will find the k2 and k3 using the classical approach as I explained in the previous problem. So again, I reshape this relation, the relation, in order to sort based on the power of s. Again, in both sides I have 3, so 3 will be cancelled out, and I just need to put the coefficient of s squared equal to 0 and coefficient of s equal to 0. By this, k2 will be equal to minus 3 over 5, and k3 will be equal to minus 6 over 5. So x of s is in this form. If you look at here, I have minus 3 5 s and minus 6 5. I further expand minus 6 5 as minus 3 over 5 and minus 3 over 5, and I separate the fractions. If you look at denominator, we need to rearrange the denominator so that to find a shape of cosine or sine Laplace transform. To do so, I have s squared plus 2s plus 5. I split up 5 as 1 plus 4 and rearrange it at s squared plus 2s plus 1 plus 4. So I have s squared plus 2s plus 1 as s plus 1 power 2 plus 4. So the x of s will be in the form of 3 over 5 multiplied to 1 over s minus s plus 1 s plus 1 s squared plus 4 minus 1 over s plus 1 s squared plus 4. Again, I just factor out 3 over 5 from this relation. I further, for the last component, I multiplied by 1 over 2 and 2. I will explain why do I need to do that. If for this to find the solution of Laplace inverse of this one, I need to use these two formula. Laplace of e power minus 80 cosine bt is equal to s plus a over s plus a squared plus b squared, and Laplace of e minus 80 sine bt is equal to b over sine plus s plus a power 2 plus b squared. The reason that I reshape s squared plus 2s plus 5 in this form is that I want to use this formula. So if you look at this, the relation for x of s, the Laplace inverse of x of s will be, for the 1 over s is a unit step function, will be 3 over 5. For this one, if you compare this fraction with this relation here, we see a is equal to 1 and b is equal to 2. So the Laplace inverse of this fraction will be equal to minus 3 over 5 e minus t cosine 2t. And for here, the reasons that I multiply to 1 over 2 and I did this calculation 1 over 2 multiplied by 2 because I wanted to reshape this fraction to this form, to the form of the e minus 80 sine bt. So the Laplace inverse of this one will be minus 3 over 10 e minus t sine 2t. Since we are looking for the final value of the x of t, we can get the limit of x of t when t goes to infinity. By putting t equal to infinity, e minus 80 will be 0. So these two components will be 0, and the final value will be equal to 3 over 5. In another way, I can use the final value theorem in order to calculate the final value of x of t. The final value theorem says limit of x of t when t goes to infinity is equal to limit of x of s when s goes 0. So I have x of s here. If I multiply to s and take the limit, I will have 3 over 5 s multiplied to this factor. By getting the limit when s goes to 0, the final value will be 3 over 5, which is exactly the same as the value we got from limit of x of t when t goes to infinity. So you have two approaches: one, to directly calculate x of t and take the limit when t goes to infinity, or use the final value theorem and find the final value for x of t. So the two important points for this problem is to know how to use final value theorem and how to use these two relations for the Laplace inverse of cosine bt and sine bt. In the last problem, I would like to find the response of y of t, which is the displacement of the cart M. I have two components, one spring and one damper. To solve this problem, the first step is to draw free body diagram and assume that y is bigger than x in order to properly draw the free body diagram. For the mass M, the first force acting on the mass M will be a stiffness or a spring force, which its value is equal to ky minus x. Again, because I assume y is bigger than x, it means that a spring is stretching and the force is opposite to direction of mass M. And for the damper, for the damping force, the damping force is b multiplied to y dot minus x dot. Again, since I assume that y is bigger than x, it means damper is stretching, and damping force is opposite to direction of the mass M. I have one more component force, which is inertial force. The inertial force is equal to my double dot. The inertial force here is my double dot because y is the global coordinate, or it is measured with respect to ground. So by adding this force together, I will have mathematical model of this system as my double dot plus by dot minus x dot plus ky minus x. I reshape this formula or this mathematical model as my double dot plus by dot plus ky equal to bx dot plus kx. I take the Laplace transform from both sides. I have ms squared ys minus sy0 minus y dot 0 plus bsys minus y0 plus kys equal to bsx of s minus x0 plus kx of s. By assuming the initial condition given in the problem, I have y0 equal to 0, y dot 0 is a, and x0 is 0. Why x0 is 0? Because the input is a step function, and for the step function at time t, the function is 0, and for the time bigger than 0, it is a constant value, and for the unit step function the value is 1. So if I rearrange this relation, I will have ms squared plus bs plus k multiplied to y of s equal to bs plus k x of s plus ma. I just brought ma to right hand side. So if I can find the y of s, if because the input is the unit step function, the Laplace transform of the unit step function will be 1 over s. So the resulting relation for the y of s will be in this form. The question asks for the final value of y of s. Finding the Laplace inverse of this one, because we don't have the value for the k, is a little complicated. To find the final value, I use the final value theorem, which says the limit of y of s when s goes to 0 is equal to limit of y of t when t goes to infinity. By doing this limitation, I will add do the s multiplied to this fraction and s to this fraction. If you see, this s will be cancelled out with this s, and if I put s here 0, 0, and here 0, I will have k over k, which will be equal to 1. And if I put s here, I have in numerator mas, which if I put s equal to 0, denominator will be 0 and denominator will be k, so 0 over k will be 0. So the final value of the response will be 1 plus 0 equal to 1. Okay, I hope you find this micro video help you to solve the problem. If you have further questions, please feel free to come to my office. I will be happy to answer your questions or send me email. And at the end of this micro video, there is a questionnaire. I would appreciate if you fill up the questionnaire and help me to improve the approach for tutorial sessions, and in order to improve the presentation during using micro video tutorial. Thank you everyone, and have a good day.